Hello and welcome back to my series Mastering GenAI with MLflow. In today's episode, we're going to concentrate on how to build a complete RAG application by using all the MLflow instrumentation that we actually have. This particular notebook is going to cover an end-to-end application of how you actually fully instrument and develop a RAG application doing construction all the way to deployment, how to do end-to-end tracing with complete MLflow's APIs, and we do some performance analysis and optimization to figure out where are the bottlenecks and what we can actually do to improve. And then finally, we're going to end with having built the entire end-to-end application with all the instrumentation. How do you now actually evaluate your queries to make sure that they're relevant, they are faithful, and they answer the questions that you actually wanted to supply them? So this is sort of a core component of any particular RAG application. You have the embedding system where you put all the documents in a vector database. You have a retrieval process whereby your queries are going to create embeddings, and they will do some sort of an algorithm, either cosine similarity or some of the production ready algorithms to do the similarity matches, and then you'll get the top 4 documents. They are retrieved, and then those documents are then passed to an LLM through a complete generation of the answer. And then finally, we want to evaluate whether the answer was correct based on the query and based on the information or the documents that we retrieve. So basically, we're going to instrument quite a bit of the code. A lot of the instrumentation is going to be based on the functions that we actually write. So the typical user query that actually goes under the transformation is that you have a user query that's going to ask a particular question that you want your RAG application to fetch the document and augment that with the additional information, asking the LLM to compose and create an answer. So the first thing you're going to do is you'll have all these different functions that are going to be part of your span operations. You're going to validate the query, and the query could be span, could be a PARSER span tag, could be something like the length or the content check to make sure that the query doesn't have any harmful content. So that would be sort of one way to customize the validation of the query. And we're going to target, or we're going to attribute that span as a span attribute of type parser, and we look at the code and see what it actually means. The next thing we're going to do is we're going to embed the text, and the embedding the text means that we're going to take the particular query and then create vector embeddings to then go ahead and do the searching where necessary. Then we're going to do a semantic search for that particular query against the documents that we have already indexed, and we'll see how those documents are indexed. And here we're using a similarity or cosine similarity to get the top X index. But in production, you might use sort of more custom-based or even more production-ready cosine similarity. And then we're going to assemble the text. By assembling the text, what we mean by here is that we're going to take the documents that we actually retrieved, and we're going to create the context and then send it for using our prompt to the LLM to generate the particular response. And once the response is generated, we're going to again parse the response to make sure that it has the right content, it doesn't have any harmful content. This could be some quality checks, this could be some custom checks to make sure that it doesn't have any PII. And this entire flow, you can actually see, is what we call a trace. And each trace will contain a span, and then the entire trace, or this entire chain, is what we call a RAG pipeline, and is going to be tagged as a chain span. And anything that we actually happens in this particular chain is going to be tracked. So we're going to be doing experiment tracking, we're going to be doing span level tracking, we're going to do token and cost metrics to find out how much this actually costs, what's the latency per step, what did we actually do any cache hits. And we're going to use that particular strategy to make sure that we efficiently use the cache to fetch that from the cache rather than getting from the store. If the embedding for the query is similar or we have seen something, we can use that. For document store over here, we're going to use an in-memory preempted document, and we'll see how we actually do that. But in production, you would actually use some sort of a real-time vector database to do that. This particular tutorial is for pedagogical reason, and we just want to make sure that you understand the concepts of what's involved in building an entire RAG pipeline. So let's get started. Okay, as I said, we're going to be doing a lot of tracking. So they'll be tracking at 4 different levels, or 3 different levels rather. We're going to have an experiment level where we're going to be logging the model configuration, because you might be using a couple of different models to be actually doing the RAG, one for the embedding and the other one for LLM context and getting the conversation constructed. And then finally, you might set some hyperparameters of how many documents you want to return. At run level, we want to track on individual queries, what are the input, what are the output, what are the performance metrics, how much did it actually cost per query, and the query can be how many tokens we actually used and what level of latency we actually require. So these are sort of a good way of understanding and instrumenting your particular RAG, so then you can find out the appropriate bottlenecks at each and every level and address them as you go along. So let's get started. As I say, this is going to be a full RAG system that includes all these different aspects of tracking and part of instrumentation, which is very much a typical what you actually do in a typical RAG system. If you have not used if you haven't gone to any of the previous modules, make sure you actually go through 1 to 8. This is the 9th episode, so you understand what tracking and tracing is all about. So let's get started. For brevity, I actually ran this particular notebook ahead of time, so we don't have to sort of wait for things at the churn. I'm running this on my local host, so I'm going to be using my OpenAPI client keys. My judging the model for evaluation, I'm going to use the ChatGPT 5.2. The edge model is going to be 5.2. Again, this is going to be a model that's going to be taking the prompt, taking the document's context, and then creating the generated answer for the user. And then my evaluation judge is going to be, again, this particular URL. I'm using OpenAI autologging, so anything that I interact with the outside LLM is going to be tracked, along with all the stuff that I do with auto tracing. So we'll see how that actually works. Okay, document store and embedding. This is an important part because the core of any RAG application is that you actually have a document store that you create embeddings and you store it. In production, normally, if you have a large corpus, which is made of different heterogeneous documents such as text and MD files and PDFs and HTML, you probably want to use a production-ready vector database. But here, since this is the pedagogical tutorial, I'm just going to use a very homogeneous document of documents that I actually have created. And we're going to use a document store of about 11 documents, which are going to be indexed using embeddings, but they're going to be using, instead of using a vector store, we're just going to use an in-memory store. That way we get an idea of how you actually create a document store in real life. So these are a set of documents that I just picked up from the MLflow documentation, and I've just created some paragraphs over here that we're going to index, and we're going to query against this to see how a RAG application serves indexed queries and then returns you the topmost documents that actually were most similar to the query that you presented. So here are my documents that I actually have, about 12 of those, and then we're going to create embedding for the query. Now here is a function that's going to take each and every query and it's going to embed that. And I have created this particular function and I've decorated that as a trace because we want to make sure that each and every operation within a RAG is traced, and the one way to do that is by having what I would call a granular trace. And over here we're going to have a name called embed the text, and we're going to declare that span type embedding, which means that this is a type of a span that was used to embed a particular query, and then this way we can actually track how long it took, how many tokens were used. So we're going to use sort of create a cache key of that particular text, which is the query that actually came in. We're going to hex digest. We're going to get the current span. Once we get a current span, we're going to check to see if that particular query, we have seen it before. If you have seen it before, we're going to set that attribute to be a cache hit. And we're going to set some of these attributes and we'll look at into the MLflow UI later on to see what I mean and what they look like. I'm going to go ahead and create a particular embedding over here. I'm using OpenAI text embedding model to actually create vector embeddings for this particular response. Once I get the response from my thing, I set the attribute and I put it in the cache. Very simple. All it's actually doing is taking a query, creating an embedding using OpenAI embedding model, taking the particular list of vector embeddings and then putting that into the particular cache using the query as an MD5 index into the cache. So this is kind of our in-memory store. The next thing we're going to do is we're going to compute this particular embeddings for each and every document that we actually have. So this is iterating through all the documents and creating all the vector embeddings for those. So here we're going through the entire embedding of the document. We have about 12 documents. What will happen in production, if you actually had this, you will actually have to go through some database that have your corpus. It's going to create that, create chunking, create all these different strategies that actually use to create a vector database. Most of the production database like PyCon, like VectorDB, like Databricks Vector Store have built-in algorithms that allow you to do chunking and have very efficient algorithms to actually create those embeddings and doing a kind of an overlapping so you actually have a consistent flow of embeddings in your vector store. So one thing good about running this in the notebook is you actually get the output of all this. I have about 12 of this query queries. Most of them were embeddings. This is what this kind of output looks like. We'll look at it more in detail when we look at the output of this particular thing. All right, so here we have expand the trace. This is embedding. We have created embedding. This actually gives us the MLflow tracing of what it actually each and every trace looks like for that. Step number 4 is going to query the processing and validation. And this is one of the steps that we actually saw in that particular flow. And again, this is going to be another function. And the reason we defined in this as a function is that each and every part of that particular pipeline is a function called that is a span. And over here, we're going to use that as a span type parser. We're going to validate the query. This could be something validation you actually know you want to do. It might be custom validation. You might want to check the length of the particular, you might want to check for some special characters. You might want to check for PII. All that particular information can be done by validating the contents of the query that actually comes in. So here we're going to set the attribute length. We're going to check whether what the minimum length is. We disallow query anything that's actually bigger than that, or we're going to truncate that particular query. We're going to set the attributes so we have some sort of metadata for what sort of query was sent to us and what sort of query we processed, and then we just return a dictionary that has this particular attributes. So that's another function. The other function in that particular entire workflow is how do you actually do a search with similarity scoring. And as I said, for a small or homogeneous corpus, cosine similarity is a good illustration algorithm when you're teaching somebody how to actually build a particular pipeline. But for a larger, as I earlier say, for a larger and heterogeneous corpus, you probably want to use PDFs. If you have a larger corpus, as I say, such as PDF, text, and HTML, use industry standard retrievals such as BM25 or BM25F, dense nearest neighbor vector. These are all proven algorithms which are more efficient, and they normally come with vector databases or proprietary vector databases that gives you the API to actually create this particular embedding in a more efficient way. But we're not going to use that because we have a small corpus, and this is mainly for illustration of how would you take a RAG applicant, instrument this so you have an idea of how the workflow actually worked. So searching is an important part of that. When you actually get a query, you're going to search that. So these are our query embeddings, which embeddings for that particular query. This is the documentation embedding, all the entire document store that has all the vector embeddings for that particular entire corpus is one of the arguments. And we are asking to return us the top 3 documents that has the most cosine similarity vector to that, and our minimum score is that it has to be about 7.7 or 70% of similarity match to get us the 3 documents. So we're going to set some attributes over here. This is an important part of instrumenting so that we have an idea of what metadata was part of this particular query, and then we're going to compute the cosine similarity, and this is an algorithm that actually computes the cosine similarity. That you take a vector embedding and you go to the corpus embedding and you find what is the nearest cosine angle that is similar to the vector embedding. And this is something that if you actually are familiar with vectors, this is how cosine similarity between 2 vectors are actually computed. The closer they are, the similar they are. And there are other algorithms that actually give you the ability to show that. So we create a filter embedding, and then we return the most top 3 documents that actually matched to a particular query. And then we have the results over here where we actually send back. And then these are the attributes. Again, we store that in the metadata so we can actually have an idea of what was the average score of a hit or of a score for queries. So that's a function that's going to search this query. Once we issue a query and we search the database, we get a set of documents. We're going to take that particular document and then create a prompt and then give it to LLM to compose a nice formulate answer of what the query is. So this is what the part is. And since this is going to be another span type of parser, by assembling the text, we're going to name that as assembly text. We're going to get the current active span. We set the attributes again for our metadata. If we didn't get any documents, we're just going to return the no document retrieved, which means that the query failed to search any similar documents. In other words, we don't actually have that particular stored in there. Finally, here is our prompt that we're going to ask the LLM to say you are a helpful assistant and answer the question based on the context provided. And the context over here are the documents which were fetched from the vector store. And we're going to provide the context, which is nothing but a collection of documents, the original query, and then we're going to return this particular prompt to the LLM to do that. And then finally, this is the second last step, which is not last but last to least, is the LLM response generation. And this is what generates the final response, which is well formulated by the LLM. And we're going to attribute this span as of type LLM. We're going to use the GPT model if you don't provide that. This is going to be a prompt if it was generated from a previous function, and it returns a dictionary of some key value pairs. Again, every time we actually use a span, we get the most current span. We set certain attributes that we might want to look at it later on in our post-analysis. What type of model was used? What was the temperature used for that particular query generation or response generation? And then this is where we actually now call the LLM to automatically go ahead and create a response. We have the model, we have the user, we have the content, we created a prompt, we provide the temperature, we get the answer, and then we set those attributes as metadata so that we have an idea in post-analysis to see what sort of attributes were generated and how many tokens were used and what was the total tokens. That way we can do some sort of a performance analysis. And this is finally the answer we return back to the part of the query. The answer is the original answer that was returned by the LLM, the tokens used, the model, and then what was the reason for that particular finally to finish. So that's our answer generation function defined. And then we actually also want to have some sort of a response validation and post-processing. And this is normally after the query has been generated and has been returned from the LLM. We want to make sure that the response is what we were expecting. And this could be anything that you actually see necessary to do the post-processing. And again, we're going to define this of type span parser. We're going to validate that. We're going to create some sort of set attributes, metadata, minimum length, what was the answer of the length. We're going to keep track of any issues that we detected. The reason might be I don't have enough information. In other words, the LLM returned the response or the document was not fine. I could not find the answer. These are some of the issues that you actually might want to keep track of. We create this particular thing, we put it in our attributes, and then finally we return the response saying, here's the answer, here are the issues, if there were any, and then was that a valid response? So this is kind of the post-processing. And finally, we've done that. This is how we construct an entire pipeline. And the pipeline is normally span type chain, where you actually have a sequential steps of each and every thing that we actually showed in our architecture diagram above that's going to do that. So let's see how we actually do the entire chain. We're going to validate in our step one what was the user query. We're going to validate the query when we get the result. We're going to do validation result processed. Step number 2 is going to be creating the embedding. Step number 3 is we're going to search the documents, right? The document searching is where we actually now have an embedded query, and we're going to search against the documentation vector store. We want to return the top k documents that had the cosine similarity that, and the minimum score should be about 70%, or the angle gives us the 7% similarity. Once we actually have those documents, we're going to go ahead and create the context, which is step number 4. Here is the process query that actually came up fine. Here is the retrieve documents, and then go ahead and generate the answer. And this is where we actually call the LLM to give us a nice answer. And then finally, step number 6 is validate the response, and this is where we actually have that. So this end-to-end function is called RAGAS system, and see how we can actually test this. We're going to issue about 5 different queries, or 4 to 5 different queries, and each query will go through this entire step. This is the architecture diagram that we're going to go through the entire chain. So validate the query, embed the text, do the search similarity, assemble the context, generate the response, and validate the response. This is our entire RAG pipeline that was executed in that particular function. So what we've done over here is we define all this particular function. They're going to be executed as part of the pipeline. So we take each and every query, we're going to execute our RAG pipeline for that. We're going to compute the latency, and then we're going to generate some of the responses. We're going to calculate the particular result, and then give the appropriate answer. So this particular function takes each and every query and then goes through the entire pipeline and then generates the response for each and every query. Let's look at query number 1. What is tracing capabilities does MLflow provide? Here's the answer that was generated. We used one document. The document ID was 1. Here's the metadata that we actually want to keep track of. So the documents we used were 3. Document 2, document 9, and document 3. These are document IDs or reference IDs that were used to compute the cosine similarity. We got an average relevance of about 0.69, which is 0.7. close. Number of tokens were used were 625 to do both embeddings and generating a response. Latency was about 2.19 seconds, and then it was a valid response. So you can see that each and every query goes through this rigorous pipeline to generate the embeddings, search the documents, create a response, figure out how many tokens were used, what were the latencies. So this is a good way for you to sort of figure out where the latencies are and how many tokens are used. And based on that, you can actually do some performance analysis. So this is sort of the output of all the queries that were actually processed. Now we can actually do some sort of performance analysis. Now we have created and generated all the particular metadata. What is the way that we can actually use to get an idea of what was the sanity? We want to find out what was our latency. How fast is our end-to-end pipeline? Are there any outliers that signal retrieval responses or LLM bottlenecks? This is a good way for us to sort of figure out, because we're instrumenting each and every span in each and every step in that entire pipeline. What was the token usage, right? How many tokens does each query consume? If you have a huge amount of tokens, maybe there's too much of document, maybe the context is large enough. Can I use a smaller model to make sure that my token usage is minimal and I'm not costing? Is it cache effectiveness? Are the queries being cached? And if they're being cached, how often am I getting a cache hit or cache miss? This is sort of a good way to do some sort of a performance analysis. So what I do over here is I go through all the results for each and every query with the success, and then based on that we compute some sort of a success rate. We create an average latencies for the particular query. What was the minimum? What was the maximum? What was the standard deviation? What was the token usage? This sort of gives us a good idea of what the overall performance was. And my success rate was pretty good. All the 5 queries were answered successfully. Average latency of 1.8.6%. What's my minimum? What's my maximum? What is the standard deviation? And what was the token used? Average about 550 tokens. So once I'm done with the performance analysis and I didn't see any particular bottlenecks, let's assume that this result is something that's actually quite satisfactory, and we want to go ahead and now say, okay, I've done this, I've created my span, I've done some performance analysis, all my queries somehow seem to be pretty reasonable, they're not any outliers, and I now want to perform some sort of an evaluation. I want to ascertain, how did my pipeline perform? Did the RAG metrics comply with the judges that I'm going to use? Now, there are many RAG metrics that you can use. What we're using over here is the RAGAS metrics, which is more specifically for retrieval augmented generation. MLflow actually provides you integration with this third-party RAGAS metrics. We're going to use 2 of those metrics to see. One metric we're going to use is called faithfulness, which means that it measures, does the answer only use its facts from the retrieved documents, or is there some sort of hallucination, or does it actually just make up things without adding or amending information? So this is kind of how faithful it is to the document. In other words, is the LLM taking the context that we use the vector database to retrieve the similarity, and does it add any additional information? And this is normally done by looking at the traces with the retriever span as part of the function that we actually use. The other one is contextual or context relevance, and this is similar to faithfulness. Did the retriever fetch the documents that actually helped you answer the questions rather than unrelated content? So in other words, was our cosine similarity close, or was it large enough? So if I ask the question, what is the purpose of the model registry, and it gives me something completely different about prompt registry, we don't have the context relevance. Those are the 2 RAGA metrics that actually we're going to use to evaluate. So we're going to do the evaluation as usual, create this particular judge called faithfulness, given the particular model. Again, there's our third-party MLflow integration, so you can just use the APIs to create those 2 judges. And once we have done that, we're going to go ahead and search all the traces for this particular pipeline, the filter string reg pipeline. That's what was span. We're going to get the maximum results, and we're going to go ahead and evaluate those particular traces using this particular function. There's a lot of code over here, but the whole idea behind it is just doing a very simple evaluation. So this is the evaluation over here, where we're actually taking the traces that we actually found. These particular functions are sort of making sure that we have the right amount of traces that actually have the retriever output, because that's the span that we actually want to make sure that RAG metrics get that. And then we're going to get those specific traces to do the score scoring. Here are our two judges. And once we did that, we go ahead and evaluate. We get the matrix and figure out what the evaluation was. And then finally, what we actually got was a complete evaluation matrix where we got the context relevance to be pretty good. The faithfulness was mean. That sort of gives us the end-to-end workflow of a RAG. So now let's look at what the output of that particular UI looks like. So I'm going to go over here and I'm going to go to my RAG system. And you can see I have about 29 traces. My latency was, over the period of entire experiment, was about 432 milliseconds. I didn't get any errors. Here's my token usage for input, output. Output token 138 tokens per usage. And then I get my cost over time. And the total amount of cost that was used using GPT-5 was about, really minimal. So this sort of gives us an overview of our entire RAG complete system, well instrumented. But the important thing over here is let's really looking at the traces, right? So if I look at all the particular traces, I get my two evaluation judges of faithfulness of average of 1, which is actually almost 100%. And then these are the 4 queries that I issued, or 5 queries that I issued, and I got a response for it. But before we get into that, let's look at what actually happened with all our functions. So these are our embeddings. If you look at, for example, of a text, this was our document. As you can see, it actually created all these embeddings. These are the embeddings which are actually created by the function that we actually did to create the document. We can look at the details of the text, how long it actually took. It gives us a graph. So that's the text embedding. Let's look at what our query now looks like. We can actually look at this particular query to see our entire RAG pipeline. This is sort of a good graph and good span operation that tells us end-to-end what our chain is. The first thing we did was we validated the query. So this tells us what the inputs were, what the outputs were, what the query was, what was the response by the judge. Faithfulness was 1. Gives us the feedback of why it was 1. Contextual relevance, again, we got the response to be 1. And if you look at this, validate the query, we can actually find out what was the query, what was the original query, what was the response. I can look at all the attributes that I assigned. My original length was 40. My process length was 40. Validation was true. Remember, these were the attributes we were actually setting. This is my outputs for the embedding. I can look at the embeddings. I can look at its attributes. Tells me what model was used. Here's my generated response that actually tells me what my input was. This is my instruction for the prompt, my model, my temperature. This was the output by the LLM. Any attributes that I set were set over here. So this is sort of a good way to figure out what my latency were. I can look at my token usage. I can look at my cost. I can even look at individual span, how long actually each of these individual span took. And this is a good way for me to figure out where the bottlenecks are so I can actually figure out and do some troubleshooting. So this was sort of an end-to-end figure out how do actually we instrument our RAG application. And we looked at the output and we get an entire RAG pipeline detailed into each and every span, how long it actually took, what was the expensive, how inexpensive it was, what tokens we used, and so on and so forth. So just in summary, this particular notebook sort of is a pedagogical tutorial that gives you how you actually instrument a RAG application from end to end using MLflow's brilliant APIs for observability. We use the cosine similarity just for the illustration and in-memory document database. Normally in production, you would actually use something like a vector database and its algorithms to do the appropriate embedding. We used different types of span for our pipeline, which resulted from embedding to retriever to LLM to parser and chain. So this is sort of a good way to use the MLflow to get some granular traces and span operations for our entire pipeline. We got custom attributes. We got good metadata to figure out what were our downstream analysis resulted. And then, key takeaways is that whenever you're building a RAG application, you actually want to use RAGAS evaluation and then use the span that actually has the retriever type, because that's where the RAG metrics looks for. We use the RAGAS reads and traces. We didn't use the database because faithful powerful than the contextual relevance actually looks at the traces rather than having an additional predict function or rather than having an additional database. This can be done through, again, more efficient cosine similarity metrics. In production, probably you're going to use swap the document store with something like Pinecore, Viviette, or CronDB, or even Databricks or Vector Store that actually gives you all that part of it. So thank you for joining, and hope to see you for my last tutorial in the next episode. Thank you.